Okay. Okay, now, so what's the, I'll try first to give you an overview, so apologies if this is known things for some of you, so about where do we stand now, okay, because trying to have a look at the future, okay, so to introduce the discussion later. So first of all, let me talk about neutrinos, okay, so let's focus for the moment on active neutrinos. So active neutrinos in the standard cosmological model, they have a fixed thermal history, in the sense that the thermal history of active neutrinos doesn't have any degree of freedom. Okay, everything is fixed by the by general relativity. Okay, so by the expansion, as long as the reheating temperature is large enough. Okay, is above a few MeVs, plus the standard model of particle physics. Okay, so if you don't give away any of these, the thermal history of the neutrinos is basically given. Okay, and you have only one degree of freedom. I mean, again, it's not related to the thermal history, but I mean, in the neutrino sector, which is the neutrino mass. So today, I'm not quoting, a precise number, but let's say that from the combination of present cosmic microwave background experiments plus baryon acoustic oscillations, we have a constraint on the sum of the masses, which is in the ballpark between 80 and 120 millielectron volts. So how do we know that? Most of the constraining power, even though it should be more precise, let's say most of the constraining power from the CMB, okay, comes from the effect on structure formation. So the effect on neutrinos on structure formation was studied starting from the 80s on both sides of the Iron Curtain. So on this side, I want to recall, there was a classic paper in the 80s by three gentlemen who are in this room, so Bond, Efstatio, and Silk. And then there were also a later paper by Bond and Zalai that were basically noticing how, given the large velocity dispersion on neutrinos and the fact that they are ultra-relativistic for most of the history of the universe, you have this peculiar effect, okay, in the formation of structure. So the universe on the left has a roughly 2 eV neutrino, the universe on the right doesn't have neutrinos, and you see that the universe on the right is clumpier, okay, than the one on the left. And that's how basically you can constrain the mass of the neutrinos from the CMB. And this is something that changed with Planck. Okay, with WMAP we were still mostly constrained by the expansion history, by the effect of neutrinos on the expansion history. With Planck, the structural formation, so the lensing from the point of view of the CMB, is more important in giving you the neutrino masses. Actually, now that we have the BAO are kind of giving also more power back to the expansion history. But by the way, and this is the same thing, just seen in Fourier space. Okay, so again, if you have a universe with neutrinos, the heavier the neutrino, the more it contributes to the energy budget of the universe. And then you will see this characteristic, if you look at the dashed lines, you will see a characteristic damping of small-scale fluctuations. Okay, so this is again the relative power spectra between universe with neutrinos and one without neutrinos. Okay, now why this is important from the point of view of particle physics? So we know that we know from oscillation experiments that neutrinos have a mass. There are two possibilities which are called for the ordering of the three mass eigenstates, which are normal ordering and inverted ordering. Given oscillation experiments, we know that there is a minimum value for the sum of the neutrino masses, which is 60 millielectron volts for normal ordering and 100 for inverted ordering. So what's the situation from the point of view of the lab? We have the measurements of the beta decay of tritium that put an upper limit on the sum of neutrino masses, which is of the order 1.3 electron volts. So this is an order of magnitude larger than what we get from cosmology. Of course, this is a very robust, very model-independent measurement. The one from the lab. Cosmology has its shortcomings. Okay, but still, again, that you are one order of magnitude apart. Again, if you take lambda CDM at face value. Now, we heard about this somehow yesterday, so you might have heard that the new BAO data from DESI, they're really pushing the the constraint, the upper limit on the neutrino mass is very close to the minimum value that is allowed by oscillation. So you get these limits of roughly 60 electron volts that excludes inverted ordering at some with mild statistical significance. But the problem is also that the posterior, okay, if you look at the plot on the right, is actually quite peaked in 0. Okay, so this is somehow excluding, if you want, normal ordering also, okay, to some extent. Or if you want, this is telling you that there seems to be some tension once you put the DESI BAO data into your fit. This is giving you some tension with laboratory experiments. And this is basically the same thing that drives the preference for neutrino mass. I mean, whatever is causing this is the same thing that is causing the preference for dynamical dark energy. In fact, once you fit, including also the dynamical dark energy, this thing here becomes more consistent with the laboratory bounds. And people have also been trying to somehow extend this to negative neutrino masses, where this is actually means that you are somehow, again, you are inverting the effect on structure formation that neutrino will give you. So when you go to negative neutrino masses, you are basically increasing clumping instead than smoothing out density peaks. And actually the maximum of the posterior is, again, at some negative neutrino masses, negative value of the neutrino mass. Now, let's go to the other important parameter for neutrinos, which is the effective number of neutrinos. The effective number of neutrinos is basically just a measure of the energy density in light species in the early universe. Okay, so this is the definition. Most of you will be familiar with this. As I told you, given that the thermal history of neutrinos is fixed, we have a precise prediction for this number, okay, which is 3.244 for 3 active neutrinos. It's not exactly 3 because again, the thermal history is, because neutrinos are getting some entropy from electron-positron annihilation. And this is an important parameter. Why? Because it's a probe for basically everything non-standard, okay, that happens in the early universe. Okay, so that might be either additional species or might be non-standard physics on neutrino decoupling. For example, it's enough to keep the neutrinos slightly, coupled for slightly more time to the electrons. So this is something that might happen in some beyond the standard models of neutrinos. Then the neutrinos will get more entropy from electron-positron annihilation than they do, and you will get a larger value of an effective. And sorry, the effect of varying an effective on the spectrum is basically to changing the damping tail. So because the silk damping the silk damping scale is changing because the age of the universe after recombination is changing, and also to introduce a small phase shift in the peaks. Now this is important because the damping effect, so the changing in the silk length, that's basically a gravitational, a background effect, because that only depends on the age of the universe at recombination. While the shift in the peaks depends on the fact that neutrinos are free streaming at this time. So this is the present situation. We have a 5% precision measured from Planck, and this is a more precise measurement that you get from Planck, and there is intact data plus BAO, so the values are consistent among them. They are consistent with the standard model prediction, okay, within 1 sigma basically. And a way of using the information on an effective is this plot. So this was introduced in a paper by Daniel Baumann, Dan Green, and Ben Wallish, and it was quite quickly adopted by cosmological collaboration. So the Planck 2015 paper, I think, was the first collaboration paper to show this. So here you have the decoupling temperature of a. So here we are, now I'm focusing not on neutrinos, but on additional beyond the standard model species. So if you have another species, okay, that was in thermal equilibrium at some point in the very early universe and decoupled at some time, which is what happens to neutrinos that decouple at 1 MeV, okay, if you have something similar just with a different decoupling temperature. This might be, I don't know, an axion if you want. Then depending on the decoupling temperature, you will have a contribution on delta N effective. The higher, so the earlier the species decoupled, the lower the contribution to N effective will be. And if you want, this decoupling temperature is in turn inversely proportional to the coupling of this particle to the standard model. Okay, so particles that couple very weakly will decouple very soon, okay, at high temperatures. And you see you have this growing function of the decoupling temperature. And again, once you have an upper constraint on delta N effective, which is the deviation of N effective from 3.044, you will get basically a lower limit on the decoupling temperature. So we already know that if there was a species that was in thermal equilibrium in the early universe, it has to decouple above 100 MeV, which means above the QCD phase transition. Okay? And the nice thing is that, again, you can use this decoupling temperature, again, as a probe of the interaction. Now, the exact relation depends on your particle physics model, okay? But if you take, for example, a 4-point interaction, so interaction mediated by a very heavy particle, let's say heavy with respect to the temperature, to the CMB temperatures, as it's the case for the standard neutrinos, which the particle involved are the weak bosons. So if you look for that kind of interaction, let's say, just with different particles, this decoupling temperature has this dependence on this capital G, which I will tell you what is this now, times the Planck mass. And this capital G is the dimensionless coupling, which is what enters in the fundamental Lagrangian that is describing whatever interaction these particles have with the standard model over the mediator mass, everything squared, okay? And you can use these basically to put on the same plot, let's say, constraints that you get from CMB experiments and lab, okay? So this is an example, this is okay, this is slightly different because this is what we get when we go back to standard neutrinos, okay? And let me say this in another way. So for the moment, I've been focusing only on the mass and on N effective, okay? Now, these species are usually free streaming, okay? Because again, they have very weak interactions. But for the standard neutrinos, might be the case that they have additional interactions beyond the standard model that I shouldn't move, right? Beyond the standard model that change the free streaming nature of neutrinos, okay? Now, if you do this for the active neutrinos, so you introduce some non-standard interaction, you have that, again, and you think of an interaction which is basically, which is mediated by a massive mediator, okay? You can put constraints on this capital G, and you can put these constraints on the same plot, okay, as the constraint that you get from laboratory experiments. So this is something that was done within the ACT collaboration. I participated to this analysis, even though I'm not a member of the collaboration. And again, you see that you can put this in this plane of the interaction strength and mass, and you have some constraints like this one, okay, that come from laboratory experiments, from the decay of heavy leptons, and you can put them together with the cosmological constraints from Planck plus ACT plus BAO, which is this straight diagonal line here. Another thing that I want to stress here is this one. So one might think, okay, how do we know that we have actually neutrinos in the universe? So we measure an effective is consistent with the standard prediction. So couldn't that be just another species that has the same density as we expect the neutrino to have within 5%, which is our uncertainty? So, okay, this might be strange, but then one might want to be more convinced that we are actually looking at the neutrinos. So part of the answer is here, in the sense that if I try to fit for, let's say, the collisional nature, okay, of these light particles, I will find that the free streaming scenario is the one that is preferred by the data. So if the particles weren't free streaming, okay, I should see that in the data, okay? At least if their free streaming is, unless if they are collisional, at least if they are collisional for enough time, let's say, beyond the standard model. And this is another way of looking at this. I think this is an important and nice result that was derived by Gabriele Monfalcone, Ben Wallish, and Katie Fries. And so here they are basically changing, again, the collisional nature of neutrinos in a more model-independent way. So you have two n-effective parameters, okay? So one is taking into account the effect on the background, okay? And the other one is taking into account the effect on the perturbations, which comes from from changing the collisional nature. And if you want, this amounts basically to separate, again, the effect on the expansion history, okay, which is the change in the silk length, and the phase shift, okay, induced by the presence of light relics. So here I've indicated this with gravity, which actually should be background if you want, and fluid properties. So you have these two effective parameters, and you see that basically the data are consistent with basically both being equal to 3 or 3.44. So if I had a species which has the same density as neutrinos, but is collisional, this n-effective delta phi on the x-axis, on the horizontal axis, will be 0. Okay, will be 0. While here we find, again, 3 for both parameters. Now, so let me go and have a look at the future. So first thing is, again, the neutrino masses, and this is a plot that is taken by from the Lightbird PTEP paper. And so you see that the combination of Lightbird plus CMBS4 plus BAO, either from DESI or LSST, will allow to measure even the minimal neutrino mass with a 5 sigma statistical significance. Okay, and this is due to the combination of the precision measurements of the damping tail, which is where the effect of neutrino masses is basically, because it's an effect that comes from lensing. Okay, of course with the combination with the BAO that allow you to give you a handle on the expansion history, plus Lightbird that is constraining the optical depth to reionization, because as we have heard already, there is from I think it was Marina yesterday, there is a degeneracy between the optical depth to reionization and the neutrino mass, and this can be broken again by a direct measurement, so let's say of tau, which is something that you only get by observing the largest scales. So a satellite is definitely the best way to do that. And then in that case, again, when you use a tau, a cosmic variance limited, basically tau here, you will get the field contours. Sorry, you also see here, if you want, this is a plot from the CMBS4 paper in which you see how the constraints on the neutrino mass change with changing precision on your constraint on tau. Okay, this is how the delta and effective plot will be updated with CMBS4. It will allow us, let me just tell you, since time is short, it will allow us to probe larger decoupling temperatures. And just very last slide, or maybe very last couple of slides. Here I'm focusing on something that I have done myself. So we have been talking about species that were in thermal equilibrium. So there is also the possibility that you have a very light species, okay, which was never in thermal equilibrium, okay? So this could be produced very slowly during the history of the universe by some kind of process, for example, by a decay with a very small width, okay, with a very small rate. But again, when you integrate these over a large time, you might get a sensible amount, sorry, a sizable amount of these particles. And this goes beyond, again, the thermal decoupling, thermal equilibrium and then decoupling scenario. This is called, again, freezing. This is something that you don't see with present-day experiments, okay? Because, again, the contribution to an effective from in such a scenario is too small for the present precision, but this is going to change with future experiments. And, again, I won't go too much into the details here, but for example, you might have neutrinos that have a magnetic moment. This will allow you to produce right-handed neutrinos in the early universe. And you can constrain this model, okay, with Simon's Observatory and CMBS4 to a level that is much better than what you can do in the lab right now. Present limits are already competitive with lab, and future limits will be even better. This is another model which I won't talk about, but again, this is the usual strength mediator plane, and you see that in some cases you can get something that is better than what you can get from accelerators. This is LEP, and this is the Atlas constraints. And I have just this slide that talks about the need for a synergy between small and large scales. Again, I think Martina has been talking about that this morning, so I won't stay too much on this, just telling that we need the small scales because we need the damping tail for an effective, we need the lensing for the neutrino masses, but we definitely need the large scales in polarization because we need tau. So we need the optical depth, and we need a cosmic variance, let's say a sample variance limited on a large fraction of the sky measurement of tau. I have some points for discussion, which maybe we can discuss later, but I think these are points that we should be, let's say, thinking about before we get the data from next generation experiments. Thanks, and apologies for being a bit long.
Thank you, and now Komatsu-san.
Okay, thank you very much. So here's a book that Bruce mentioned at the beginning of his talk. So this is a book edited by Jim Peebles, Lyman Page, and Bruce Partridge. This is a collection of essays from people working on CMB before 1970. And this is CMB 60. 10 years ago, there was a CMB 50 at Princeton. There, you saw many, many people in person who contribute to the essay. So I was like, these are rock stars. So I brought this book with me, and I collected autographs. This one is Peter Rowe. So who was one of the authors of the important interpretation paper of the Penzias-Wilson results. So Dickey, Peebles, Roll, and Wilkinson. I took lots of pictures with him, so that was a great time. I had a lot of other autographs. Now today, 10 years later, of course, we see rock stars again. It's great to see them again. I've gotten older as well, so what I realize now is that I see future rock stars, right? So that's something that I couldn't quite pay attention to because I was just excited to see all the rock stars, Hall of Fame 10 years ago, but now I have a bit more time to recognize that we have future rock stars. So I think our field is very good, and then let's keep going like that. Okay, so I wanted to tell you about parity violation as a new probe of the dark sector in the universe. And the overarching theme is we have lambda CDM, which requires physics beyond the standard model of elementary particles and fields. We don't know what the dark matter is. It's dark matter 92 since the Zwick's discovery. It's dark energy more or less 30, right? Since the discovery of acceleration from supernovae and galaxy surveys. And we don't know what that is now. And I was like, have we missed something? Okay, is there something that we haven't used yet? Then, yes, there is. That's a violation parity symmetry. So I wrote a review article on this 3 years ago. It's available in Archive 2. So usual keywords is cosmic microwave background. That's why we are here. And then polarization is the next thing, of course. But what's new is parity symmetry. So we saw this kind of plot The power spectra are beautiful measurements, progress over last 30 years. Is there anything we haven't used yet? Yeah. So all these power spectra are rotationally invariant, parity symmetric scalars. We have rotationally invariant, parity asymmetric pseudo-scalars, namely TB and EB correlation that you haven't seen yet. Here you go. That's the EB power spectrum. Inverse noise weighted, Planck PR4 and WMAP9. Chi-square relative to zero signal is 125 for 72 degrees of freedom. It's terrible. Something is there. What is it? So we typically assume that the polarization was generated at the last scattering surface by the action of Thomson scattering. Then electric fields, magnetic fields, basically kind of didn't change the orientation, so it propagated for 14 billion years to reach us. But what if something was happening to this light that rotated the plane of linear polarization of CMB by an angle beta? Then that's actually breakdown of parity, because angle over the full sky, that's the key, okay? Over the full sky, angle can be either right or left. If you do the parity flip, right becomes left, but we don't observe that. Because angle has to be either positive or negative. If you detect non-zero angle, doesn't matter if it's positive or negative, that's the sign of parity violation. And that will mix E and B modes. So let's imagine that we observe E and B today, but when it was emitted, there was E and B. Then because of this rotation, isotropic rotation, you get this phase factor. So E and B will be linear combination of E and B at the surface of lasso scattering, rotated. So even if there's no B at the surface of lasso scattering, there will be B generated by the rotation. If you take the product, you see that observed EB will be proportional to EE at surface of lasso scattering times cosine, the sine for beta. You can also do a little bit more math, and you convince yourselves that observed EB is given by observed EE minus observed BB. Now, if we lived in a universe where observed EE is equal to observed BB, we wouldn't be able to measure parity. But, you know, CMB is a gift. We have measured that EE is much greater than BB. So we can take this difference and then measure observed EB. A crucial thing is that this rotation predicts that observed EE contains acoustic oscillations that we measure in EE. That's a definitive prediction, one parameter family. It's a beautiful fit to the data. It's 9 sigma. Is it due to galaxy? Well, it doesn't look like so because you have a clear acoustic oscillation. But let's, cut more sky and see if the signal is isotropic over the sky, and it is. It doesn't matter what sky fraction you use, the angle is the same. So this is not foreground. Absolutely not, okay? Foreground will contain no acoustic oscillations. Good. What is it? So here comes a tricky point, because we can't actually distinguish between whether the angle was rotated by some kind of cosmological effect and angle was rotated by me. Like I tilt my head. Then I break parity. This or that. Right? So I generate artificially the polarization rotation. So you have to do calibration of your instrument, optical system, to make sure that you are not fooled by this miscalibration angle alpha. When we're doing this measurement, both WMAP and Planck stopped operating. They left L2. They became satellites orbiting Earth, the orbiting Sun. We can't send Bruce Willis to calibrate it again, so we're stuck. Okay. So we used physics. So this cosmological rotation tends to accumulate over distances. So, for example, if you have an interaction between scalar field and photons in a parity violating manner, scalar field is slowly rolling, then this effect is proportional to the path length of the photons. If you take that point of view, then we conclude that, okay, this angle can be rotated by cosmological action for CMB, but not for the galactic foreground. Because it's right there. It's only 10,000 light years, not 14 billion years, right? So if you say that whenever we see EB in the foreground, it's most likely the miscalibration. If we see rotation CMB, it's rotated both by the miscalibration and by Birefringence, this cosmological effect, then we can break degeneracy. Of course, you have to worry about intrinsic EB, so that's the only place where foreground enters. You may be worried about intrinsic EB over the foreground, and you just have to take care of it. Yep. So if we did that, we could recalibrate Planck and WMAP. We know that Lyman Page told me that on the ground, WMAP was calibrated within 1.5 degrees. I read Planck papers. Planck people also told me that their ground-based calibration campaign accuracy was 1 degree. And look, all these redeterminations were all within the quoted ground calibration uncertainties, and we made them better. So there's nothing alarming here. It just seems like this method is working quite well. Now, because we are now decomposing 9 sigma into 2 components, cosmological rotation and miscalibration, 9 sigma became 3.6 sigma. Is it galaxy? We have 0.3 plus minus 0.9. Is it galaxy? Let's cut the sky, and no, we get the same answer. Error bar increased quite a bit because we are relying on foreground to calibrate. If we cut the foreground, we'll get less foreground, so it becomes less precise. Okay? But I don't recommend this method anymore. This is a disparate effort to kind of get more science out of Planck and WMAP. So for the future, you have to calibrate. Okay? Now, what is it? Of course, Faraday rotation can rotate the angle of polarization, but that angle from magnetic field Faraday rotation must be proportional to 1 over photon energy square. We can test this. So we parameterize angle as the function of frequency to n, and n is minus 0.2 plus minus 0.4, so we exclude Faraday rotation. We still, can't be fully sure that this is totally independent of frequency, but so far results are consistent with no frequency dependence. Then so after this, because we're always worried about unknown systematics in WMAP, unknown systematics in Planck, so Oslo team, Cosmoglobe collaboration, reanalyzed LFI and WMAP, then did this measurement, got the same answer. So, but we can't rely on foreground, no? We have to have has been said repeatedly during this conference. We need independent methods, independent measurements, independent teams, independent telescopes, independent everything. So we have that. And so ACTO collaboration used the model for optics, no foreground whatsoever. They used the knowledge of the simulated, the optics model, and they came up with this 0.2 plus minus 0.08, including systematics in the knowledge of simulations. Now, let me point out one thing. Again, this angle can be both positive and negative. The fact that both measurements are positive is already telling you something. I mean, it's 2 measurements, right? You have coin flip head, or tail, it's nothing. But it could have been that they will give you negative measurement. That's the end of the story. So all I'm saying is that the story continues, and if you just naively combine two Gaussians, anyone can do it, we have 4 sigma. Okay. So what are we worried about? We are really worried about unknown unknowns. Really the killer in our measurement is that we crucially depend on 353 gigahertz of Planck. Any unaccounted for systemass in 353 gigahertz will kill us. That's number one. Number two, acto collaboration knows that there is a systematics that they don't understand. Different frequencies within the same optics tube give you different angles by moderate sigma, like 2 to 3 sigma. They are very uncomfortable. So basically what you're seeing here is that there's a measurement that no one believes, there's another measurement that no one believes, which give you consistent answers. But of course, to give the definitive conclusion, you have to have artificial polarization sources, then you calibrate very well. So that's exactly what the BICEP 3 collaborations are doing. They have achieved a very good calibration. Simon's Observatory are doing different even the calibration methodologies for angles, and we may hear their words soon. So that will be the definitive measurement. Until then, we can't really be sure. What if it is cosmological? Then you have something that looks like a Chern-Simons term, but it's really in the standard model. This is what makes pions decay into 2 photons. This term is nothing mystical. It's there in the standard model, but this term makes neutral pion decay into photons in 10 to the minus 17 seconds. We don't want that to happen for dark matter or dark energy. The decay constant has to be much, much bigger than pion decay constant. Then we call this axion-like particle rather than pion-like particle. Then actually the result is such that if this is really truly cosmological, and if it is dark energy, it will rule out cosmological constant instantly, because it has to be dynamical. Okay? If it is dark matter, fraction of dark matter, the dark matter will be parity violating. Either way, it will be cool, and you may have this axion-like particles, Mexican hat here, potential. Maybe spaces full of axion-like particles. We'll see. Okay. So parity is a new player in cosmology, and we have some tantalizing hint of the signal, but we really have to have absolutely calibrated measurements to see if that signal is real. Stop here. Thank you very much.
Yeah. Dr. Ackerman.
Okay. Let's see if I can. Great. Yeah, let me start by thanking the organizers for the invitation. Yesterday we had a session, a panel on tensions, and also in the evening we had some discussions on anomalies. So basically my focus today is on the so-called larger scale anomalies or CMB anomalies. So, well, first of all, this is basically my own way of thinking about anomalies. So I know it's a very controversial topic, so it would be nice to have some discussions afterwards, but yeah, let's basically start. All right, so let's just start by this, very well-known way of actually talking about CMB data. So since the very beginning of CMB data analysis, we always, basically we learned how to talk about these perturbations or fluctuations by expanding these fluctuations in terms of the spherical harmonics, okay? So the assumption here, the main assumption was like, or is still, that our standard model for the fluctuations, maybe coming from inflation or something like that, tells us that the sky is statistically isotropic. And also these ALMs here are independent Gaussian random variables, all right? So assuming that, then the two-point correlation, or basically the covariance matrix for these ALMs will become like this. So it will be CLs, which are the angular power spectrum, and then you have all these Kronecker deltas here, right? So for full sky observations, all the interesting information is basically contained in this estimator that we go and measure, and that's basically how we get all the information about, like, lambda CDM, cosmological parameters, and all that, right? We have, of course, measured the angular power spectrum, and examples are here, and we know that we have a 6-parameter fit to many more data points. And this is obviously astonishing experimental accomplishment. And also it shows remarkable agreement with theory. So far so good. However, there is a but here. So again, I emphasize that we assume that the sky is statistically isotropic, and also that ALMs are independent Gaussian random variables. This was the assumption. The natural question is, shouldn't we actually check these assumptions, right? Well, this was asked, of course, many years ago. People try to see or check whether the universe is actually statistically isotropic, particularly using the CMB data, temperature data mainly. And this was checked by many different groups for both WMAP and Planck data. And some examples are these 3 papers by Planck, where we actually looked into different anomalies. Oh, well, as I was going to say, different ways of testing the statistical isotropy. And, well, this was the finding. So the finding was that there are some larger scale anomalous features on the CMB sky that are unexpected or extremely unlikely in lambda CDM, all right? This is what we call cosmic anomalies. There is a list here of some of them, like the lack of large angle CMB temperature correlations, hemispherical power asymmetry, quadrupole and octupole alignments, point parity anomaly, the cold spot, and the list is long. So today, obviously, I'm not going to go through this. I'm assuming that all of you know what these things are. I don't have time to really go through them. But the point is that if you compute the p-values for these anomalies, they're typically less than 0.1%, okay? And the important thing is that almost all of them, at least to me, except for maybe the cold spot, are basically an implied violation of statistical isotropy, one way or another. I'm just, so if you're interested, of course, there are some review papers on this, and I'm just advertising one review paper we are working on for physics reports, and stay tuned, and that we're going to include almost all of these cases. So, I think by now, almost everyone agrees that these are real features on our CMB temperature sky. And they are not instrumental noise or some foreground effects. Well, one simple reason is that, for example, both WMAP and Planck found them. They have different noise strategy, basically scanning strategies. And also, we know, for example, from Planck that all component separated maps also found them. So probably it's not because of foregrounds. So the natural question is, should we actually care? Are they hints of new physics? Okay? So recently, we looked into some of these anomalies. The question we asked was, okay, so we have these anomalies, and each one of them is maybe around, I don't know, between 2.5 sigma or 4 sigma significant. But what about like the joint probability of these things to happen? Okay, so we just picked 4 representative anomalies. So the lack of large angle correlations, odd parity preference, low northern variance, and quadrupole octupole alignments. Each one of them have these kind of low p-values. And we looked at the joint probabilities in the Planck data. So the question we were asking was, are they correlated in the tails of their PDF, the distributions, okay? Because that's where they are. And also, also what is their joint p-value? One thing that I want to emphasize, and we can discuss that, we tried not to cherry pick anything or fine tune anything. we basically took the statistics that we used exactly as they were being used before. Other groups were using them. We just picked them and just work with those. We did not change anything in there. This was a paper we wrote. It's controversial, but okay. So what we found was that the joint probability of all of these 4 anomalies basically occurring by chance in lambda CDM is less than around 10 to the minus 8. So this, we claim, would actually give higher than 5 sigma significance. Okay? So again, this is what I think. We can discuss this later, but I think, or we think, that the sky appears not to be a typical realization of a Gaussian random statistical isotropic field. I know it's a big claim. So let's see, for example, what we found. So if you look at these 4 statistics and their significance, and also like p-values, and also their correlations, these are these numbers in blue. They are showing the correlations between each of this, each pair. So you see, most of them are actually quite small, the correlation factor. Okay, except for one case here, which is also not very large, but it shows some kind of correlations. You can also look at like correlations, between pairs. Like these are between the statistics, and these are between pairs and the other statistics, and you can see similar things. So this is the triplet correlation, and this is like pairwise correlations. So it seems like these anomalies are not highly correlated. So yeah, so the question was, are these anomalies correlating on the CDM? And you can see the joint probability for all of them to happen in lambda CDM and the correlation factors. So the answer to this question is that, well, only weakly, because this factor is actually much lower than like 100, and then that means that the joint probability is actually higher than the minimum, basically p-value probability that you can have in there. So our conclusion here is that the Gaussian random statistically isotropic universe is falsified at larger than or higher than 5 sigma in CMB temperature correlations. All right? So of course, there is always this discussion. 2 points that most people raise always. The first one is, well, we cannot believe data without a model. So you cannot really falsify a model without an alternative. We can discuss this later. I'm not going to go through that, but I strongly disagree with this argument, this statement. We can discuss that. The next one, which is I think makes more sense, is the question of look elsewhere penalties or look elsewhere effect. So the point here is that you can always find anomalies in statistics in any data sets. So why you're talking about these ones. So again, we can discuss this later, but one important thing is that the typical justification of a 5 sigma threshold for discovery, which is coming from particle physics community, is that it overwhelms even a strong look elsewhere concerns. So this is what we think, and we can again discuss that. And also the other thing is that you have the look elsewhere penalties, but we are also, I'm just putting here something we call look more closely rewards, and I think that's very important. For example, looking at this S1/2, which is about the lack of large angle correlations, look elsewhere effect might ask this kind of questions. Why you're talking about like the minimum of like 60 degrees on the sky, or why 180 degrees, the larger, why are you going to all the way to 180 degrees? Why we are working with C of theta squared, or why you are integrating over, for example, cosine of theta, right? These kind of questions. But also there is this look more closely kind of argument or reward, is that if you look at other things, for example, the polarization, look at this paper, already it seems from Planck, we seem to be seeing something similar in polarization, okay? So it's important to keep that in mind. For the odd parity preference, similar questions. Why, for example, you are using Lmax, well, we used 27, which was, used before. Why odd larger than even, not even larger than odd? That's another question. These are the penalties you have to pay. But look more closely. Well, if you look at that, you see that the first 9 consecutive pairs, these ones, all the way to 9, estimate this kind of p-value for us. and this is including the Lucas effect. So this is important to keep in mind. It's not just this statistic that is giving us this value. A similar thing for example, the low northern variance. Again, the question, why north, why ecliptic, why inside 16 that we use in these statistics, okay? So, but again, you have this kind of, this type of look more closely rewards. Well, I mean, okay, well, I have to be a bit fast, so maybe we can discuss this later if you want, but there are a few effects there as well. And similar thing for quadruple octuple alignment. Well, we don't really see how you can ask about Lucas effect in this case, but in any case, you have other types of anomalies that are closely related to that, and they were proposed before. So these are also kind of important to keep in mind. So what I can say, maybe at this point, is that while the cosmic orchestra may be playing the lambda CDM symphony, somebody gave the bass and tuba the wrong score. They are trying very hard to keep quiet about it, but we must demand an explanation. At least that's the way I'm thinking about these anomalies. So now the question is, with so many anomalies, what do we do? So, well, you have basically these two ways of thinking about them, physics explanations. So you can say these are statistical flukes in a standard lambda CDM, or you can say these are not statistical flukes, so showing some kind of, maybe there are hints of new physics. So how to make progress then? We can either test the fluke hypothesis, which by that I mean like to test lambda CDM. The philosophy here is that we assume that lambda CDM is correct, and then see how the measured anomalies affect predictions for other observables, like for example the CMB polarization, or larger scale structure data, or whatever you can think of, okay? The other way of thinking about these anomalies is that we make reasonable phenomenological extrapolations and then test those. The philosophy here is that we assume that each anomaly is physical and then guess what that implies for other observables. So, and finally, maybe this is what most people like, is to try to find a fundamental physics model and then make testable predictions for those alternatives. So one example of fundamental physics models that we think could actually explain this is this one. So what are the requirements for such a model? The first thing is that we need to break a statistical isotropy. So that means that we need to generate non-zero off-diagonal elements in harmonic space 2-point correlation. So we actually need to get off-diagonal terms for this quantity. The other thing is that we need to affect the scales that were causally disconnected until recently, because they are kind of like, they were outside the CMB, well, the horizon by the time of the CMB, so we need to do that. It turns out it is very hard for microphysics to satisfy both these conditions, okay? So we think at the moment that our best bet is basically to change the boundary conditions of the universe, and that takes us to the topic of cosmic topology, which is something that we have been trying to study. One example, I'm just listing 18 possible flat topologies, Euclidean topologies, just an example, and you can see that almost all of them except for, all of them except for the covering space or the, the trivial topology is basically breaks isotropy. So it provides possibilities, okay? You can also see that in terms of the covariance matrices. You see all these off-diagonal terms for one particular example, which is what we call E2, and you can see all these basically features that you can generate. So with that, 3 years ago, we created this collaboration, what we call COMPACT, Collaboration for Observations, Models, and Predictions of Anomalies and Cosmic Topology. And this is a long-term program, maybe like 10 years or 15 years. So we want to use all the cosmological data, CMB, large structure, 21 centimeter data, whatever, to understand cosmic anomalies and to discover the topology of the universe, or demonstrate conclusively that discovering this topology is beyond our reach for the foreseeable future. We have been given money by NASA for like 6 years so far to do this, and that's basically the beginning of our work. So you can look at this paper where we explain our goals, motivations, and search strategies, but again, this is just one possibility, right? Which we are interested in. So let me conclude. So There are large-scale anomalous features in the CMB temperature sky that are unexpected or extremely unlikely in lambda CDM. These anomalies are real meaning that we think they're there, I think many people think they're there, and are not just this instrumental noise or foreground effects. Their significance is between 2.5 sigma to maybe around 4 sigma individually, but their joint significance in the tails of their distribution is higher than 5 sigma. It's very easy to go above that, okay? The typical justification of a 5 sigma threshold for discovery is that it overwhelms even strong look elsewhere concerns. Almost all of them imply violation of statistical isotropy, which is very important because they are different kinds of statistics, but they're all basically talking about one thing, right? Effectively. One can and should study them further by testing the standard lambda CDM model, by making phenomenological extrapolations, and by finding fundamental physics models. That's the goal. We need to study CMB polarization data as well as other cosmological observables like large structure, 21 centimeter data, and all that to shed light on the nature of anomalies. And I would say the main conclusion, at least here, is that we should continue studying the anomalies and we should try to find more. So with that, I'll stop there. Thank you.
So I imagine there must be plenty of questions, but I would demand if Paolo, you can stop us when you feel it. Questions? Yeah.
I have a, is this on? Yeah. Question for Yashar. That you'll be expecting. I completely agree with your conclusions. So there are features in the CMB sky that are interesting, hints of something, and are worth following up. And particularly with polarization, that's very promising. And the reason is because you have the test already, you have new data, and then you can decide whether it's a real thing. But there's no need to claim that these are fantastically significant in order to justify that conclusion.
But they are.
But they're not. They're absolutely not. So you said that you don't cherry pick, but I don't understand what you think cherry pick means, because it's exactly what you're doing. So let me give you an example. So my name is Douglas. So I look at the name Douglas, the first letter is D. The chances of that are 1 in 26. The second letter is O. The chances of that are 1 in 26. I put together how unlikely is it that my name is Douglas, I get, how many letters are there? 7. I get 1 in 26 to the 7. That's clearly ridiculous.
But that's not what we did,
exactly
right?
what you're doing by combining several of the anomalies and claiming that it's 10 to the minus whatever. It's exactly cherry picking. And there's no need to do that because they are real things that might be interesting, but they're not on their own right now statistically significant, any of them individually, and certainly you can't combine them like that. That's not how statistics works.
It's exactly how statistics works. So let me actually tell you this. So first of all, this is different from your example because these anomalies, okay, well, I can think of 2 reasons now. So first of all, almost everything people came up with from the beginning by looking at the WMAP data and then Planck, not all of them, but most of them turned out to be actually anomalous, okay? So there are many, many examples, and these are simple examples. These are not something that you would think of, oh, how can I actually go through the data, combine things, and get something that is anomalous? So very simple question. Is one side of the sky different from the other? Okay, it's like, look at like whatever, like parity, for example, which is a super, that's very obvious. So these obvious things we looked at and we saw that most of them are anomalous, okay? So it's really, in that sense, this is not cherry picking. The other thing I'm saying is that, okay, these anomalies have been around, probably around like 15 of those. So we said, okay, all of them seem to be talking about the statistical isotropy. So even though they are in principle independent, but they are all talking about the same concept. Let's just pick 4 examples. I'm telling you, we just picked some 4 examples from this list, okay? And then we just chose the value. So in that sense, I'm saying this is not cherry picking. So of course, clearly, it's not like if you think of everything else that I could do and I didn't do, and then say I just picked those ones, yes. But these are just 4 of the ones that existed before. So if we just look at those, and the question was, are they correlated? Because that's very important. If they're correlated, you cannot really combine them. And you can combine them, but the probability is not just the joint probability will be different. So we just look at that. So I don't really see why you are saying you cannot combine statistics. You can if you are careful, right? And we try to be careful. Of course, there are some penalties you have to pay, look at some penalties, but the significance is very high. I mean, that's actually one of the reasons why particle physicists insist on 5 sigma, because it's really 5 sigma is something that is very hard to bring down by just, considering the Lucas-Lor effect. Otherwise, maybe even 3 sigma would have been enough. I mean, who said that you need 5 sigma? So in that sense, I don't think it's very easy to bring this down by paying the Lucas-Lor effect penalties.
I just want to comment on a lot of these things, anomalies or a posteriori statistics. Back then, I and George F. Darcy, we wrote a paper of looking at C of theta, the flat C of theta angular correlation on the sky. And that is mostly due to these a posteriori statistics. But actually, that's not my question. My question is actually to Professor Komatsu about your beta. So I wonder when, for the future measurement of beta, this kind of rotation angle, what is the prospect? I mean, what kind of experiment will improve that beta and will achieve something definite?
Yeah, thank you. So I actually forgot to say during my talk, but this is really, in a way, wonderful because we don't need statistics. Statistics are there. It's 9 sigma. So this is all systematics, right? So therefore, it's a wonderland for instrumentalists. So they do really good job calibrating something using their really great skill. Then you find the answer. So I just mentioned 2 examples, BICEP 3. Either they are doing or they have finished angle calibration campaign, and Simon's Observatory are doing also precisely this using multiple methods. So prospects, at least these 2, if not more. So I hope that there are other CMB experiments going on ground-based. I just hope that this will give them motivation to calibrate even better than they do now. Yeah.
I also have a question to Hiro. If it would be, let's say, if there would be birefringence due to the presence of an axion, let's say axion dark matter, wouldn't you expect fluctuations in this birefringence and
yes.
multiples? Did you look into this?
So yeah, multiple people have looked at it already using Planck, ACT, SPT, and they will be doing this for BICEP and Simon's and everything else. So there's not me, but there are other groups doing this, just that. In fact, I gave you 2 papers. Their purpose is precisely this. So, well, the sensitivity is not there yet, but it rapidly improves. This thing improves dramatically as you improve the sensitivity and angular resolution. So yeah, I think prospect for this is great. In fact, okay, in a happy situation where this isotropic signal turns out to be correct, the next question is, what is it due to, right? Is it due to dark energy? Is it due to dark matter? Is it due to domain walls? Or is it due to neutrinos? What else? Isotropy or anisotropy is a decisive factor to distinguish between different scenarios. So yes, this anisotropy is absolutely critical, and lots of people working on it.
If I can add something on what Eiichiro just said, sorry, before we go to another question, sorry, Lamon. So yeah, I mean, on this, of course, you can also look not just at CMB, but also at large-scale structures. Okay, so I'm doing a bit of advertising here, but we are doing something similar. I mean, looking at the cross-correlation between CMB and large-scale structures with Paolo, Natoli, Nicola Bartolo, Ale Gruppuso who are here, and the other people in Ferrara, Bologna, and Padua. And yes, one of the possibilities, just not the CMB, but also the cross-correlations. And cross-correlations are particularly neat in some respect, if you want to look at this.
And I just to build on what Eiichiro said, I mean, this signal is huge, right? It is larger than BB lensing. So it's not going to take long to verify or whatever.
Yeah.
Yeah, I just wanted to point out that there's an interesting connection between odd, even CL up and down and the lack of power in large C of theta. Actually, if you allow for a discontinuous C of L with up and down, you can always arrange for the power to die off at large theta. Only thing is, the only physical model I know of where I played around with was a closed universe with Z2 identification, and that naturally happens both ways for different parameters. So it's, I mean, unfortunately that's not in the archive, it's some fresh script article that, but now that it's become interesting, there is a connection you can make even without breaking statistical isotropy, where you are giving up the idea that your angular power spectrum has to be a continuous function. It will have kinks at low L's, and that happens naturally in one model, I'm sure, and there can be easily other models, I'm sure. A lot of smart people can figure that out.
So, I have a question and a comment for Eiichiro. It's in relation to this. Can you hear me? Yeah. So, it's again, imagine that this parity violation is there, and imagine that there is a real signal there. So, do you have, thinking now in models and theories, a prediction for the anisotropic part? So you are seeing the isotropic, so what can you say about the anisotropic part?
Anisotropic?
Yes.
Yeah, yes. So if it's dark matter, you first of all have absolutely adiabatic fluctuations, scale invariant. It could be isocurvature fluctuations, in which case you may have some other interesting things. If it's domain wall, it's order unity fluctuations, because you have field that falls into either plus phi or minus phi, and we're sitting on either plus or minus phi. What you see is either 2 phi or 0. So it's order unity fluctuations. We are almost there to, I think, find it, if it is there. Number two. Number three, if you have really the Lorentz violating 4 vector in the universe, then you expect to see dipole. Number four, if it's dark energy, we will see nothing. Right? So yes, I mean, this will be very, very powerful, and lots of people working on it. Yeah.
Have you done full-up simulations of how FF dual looks on the sky as the source for chi?
Thank you. Yeah. So what he's saying is that, so at the moment, our phi FF dual will rotate the
I'm not finished yet.
plane of linear polarization. But if you had this phi FF dual during inflation, this will actually excite one of the helicity states of gauge field tachyonically, and they will back react to the scalar perturbation. So this is not what we're seeing. We're seeing is the propagation effect, but you can also calculate.
Well, I know you're seeing the propagation effect,
Yeah.
but it arises from the source term, which is got the the twist aspect
Yeah,
to it.
this
And
will
so,
be-
if you, what I'm asking about, well, first of all, because it's FF dual, it's quite nonlinear.
Yeah,
And so you're seeing a highly nonlinear source term,
yeah.
which by its very nature is, pardon the expression, non-Gaussian, but it's
Yes.
non-Gaussian with a twist. And so if you actually look at the maps, can you see that clearly in them?
Yeah, so if you look at, I think what you're referring to is if you look at the equation motion for scalar field, you have box phi equals E dot B. That's nonlinear. That's what you're referring to,
No,
right?
that's exactly the
But
point.
this E dot B is a standard model electromagnetic E dot B. That's tiny.
That's standard, but you've got a more general FF dual. It doesn't have to be electromagnetic, or does it?
For this, because we are observing electromagnetic standard model, we are seeing light. So this has to be U1 gauge field. But if you are talking about early universe effect, then yes, I mean, that's nonlinear, we have to simulate, and we have done that, yeah. We have the map of scalar field, like a PDF. We're working on it.
Well, you
We are working on it.
can
We can-
discuss that later on, probably. And so, okay, the very last one.
Akira, I was just wondering whether, lensing due to gravitational waves, I mean, tensors, chiral gravitational waves, do they create something like the signal you're seeing? Because they would also violate parity, right? They will create these odd parity
Yeah, your famous
correlations.
paper, the bispectrum of,
Yeah, so that's probably, another arena, and of course we know gravitational waves exist. They are not necessarily chiral, but no one has checked.
So this effect will not rotate the linear polarization plane, right? What we're seeing is really rotation, because EB looks exactly like EE. The lensing of gravitational wave won't be like that. But this will give you additional EB power spectrum that looks nothing like what we're seeing, but that's definitely interesting. We have to look for it.
So let us thank the speakers again, and